Heyo, what's up guys? BabyBear4812 coming at you one more time. Today we're going to be solving problem number 64, the minimum path sum problem. Now I chose this one because it's currently being asked by Amazon, Goldman, Google, and Bloomberg. But more so even than just that, this is a problem that will come up, if not identically to this, in various different forms throughout your studies. So I think it's a really important one to know. I also think it's not the hardest problem out there, and quite frankly, when we kind of figure out how to deal with it, it's a very reproducible result, and it yields a trick that you'll be able to use in other problems. And so if you haven't tried it already, pause the video, go give it a shot as always, then come on back and we'll solve it together. So it says that we're given an n by n grid, which is filled with non-negative numbers, okay? So 0, 1, 2, and so on. And we need to find a path from the top left, right here, to the bottom right, which minimizes the sum of all numbers along its path. The note is that we can move either down or right at any given point. So the output here would be 7. The reason it would be 7 is because the path that minimizes the sum is 1, 3, 1, 1, 1. Specifically, if we started at the top left and then went all the way right, then went down and down. Each of these, 1, 3, 1, 1, and 1, if we sum those together, we get a 7, and that's what we're going to be outputting. So I think the problem in and of itself is pretty understandable. Now let's think about how we do this. Well, one potential way, and one I'd always encourage you to mention, is that there exists a brute force solution. Okay, so the first one could definitely be a brute force solution. Now, the brute force solution in this case entails, let's figure out every which way we can get from the top left corner to the bottom right corner. We'll calculate the sum at all those paths, and we'll keep some sort of trailing, or we'll keep some sort of maximum value, and we'll compare it to every sum, and eventually after we've computed all the values, we pick the minimum one. So brute force would be calculate all possible paths. Now, I think the code for this one would be, first off, tricky. Second of all, your runtime would be very, very high. So in terms of time complexity, you would actually be looking at as follows. So within, let's call it a 3 by 3 grid, you've got, within an n by n grid, you've got 2 to the n different ways to go down and 2 to the n different ways to go right. Or maybe we can use m and n just to keep their variables. So you'd have something like 2 to the power of n, 2 to the power of n times 2 to the power of m, which back to our grade 10 math is just going to give us 2 to the power of n plus m. So super high exponential runtime, definitely not feasible for anything more than a couple units. And space-wise, to do something like this, we probably have to use recursion, which means that for space, we have to basically have a stack that looks at any given time. I think the maximum can kind of be to be looking at almost every possible grid every possible cell, which would approach n times n asymptotically as we kind of grow. So this one's no bueno, right? This isn't really the one we want to proceed with. And again, there's a more clever way to do this. So so brute force isn't really going to do it for us. What if we do something like this? And we'll jump to the whiteboard here in a second, but what if there was a more clever way to solve this? And in particular, where you want your head to go with these kind of problems is to say, well, let's pretend, what if I was already at the end? And what if I was already at the end and I had to figure out a way to, at any given point right beside the end, get to the end in the most efficient way? So working backwards, right? So at this point, if we make that quantum leap, we can think to ourselves, well, that kind of solves, or it sounds, like we can potentially solve sub-problems, right? So if we were to maybe say, let's look at this grid here, and we were to say, okay, well, if I'm at the end here, would I rather approach, from here or from here? Say this was our only little locale. Let's say we broke it down into this little 2 by 2 grid. Well, I mean, if I approach from here, it'll cost me 1 plus 1, that's 2. From here, it would be 2 plus 1, which is 3. So I definitely want to approach from above, okay? And when we put this little quantum leap together, this is how we're going to kind of run toward the solution that we want to build. And so let's draw this out on the whiteboard and see how we can go about doing this. So let's think about working backwards for a second. We can, in essence, say this. If I was to start from the bottom right corner, no matter what, when I get to the bottom right corner, I know that it's going to cost me, 1 point just to be here, no matter what. If I'm standing there, it's got a value of 1, so we're gonna have a weight of at least 1, a path sum of at least 1. The question now becomes, if I was to work this problem backwards, well, if at every given point I selected what the optimal path would be, then by the time I reach the beginning, that would be my optimal path. So I'm gonna repeat that because this is the point that I really wanna drill in. If I was to optimize my solution at every single possible step along the way, working backwards, by the time I get to the beginning, I will have had the optimal solution. And that's really where the key is here in understanding this question and all other kinds of questions that fall within this domain. So let me kind of keep running with this idea. Two kind of maybe pieces of information we want to keep in mind. One is that if I'm in the bottom row, I can only move right. So remember, my permissible moves are I can move to the right and I can move down. At any given point, that's all I can do. So if I'm anywhere down here, I can only move to the right. If I'm anywhere up here, I can only move down. Any of these, I've got the option. I can move right, I can move down, and I need to make a decision at every single point. Do I want to move to the right or do I want to move down, right? So let's think about this. I know I gotta populate this value right here, okay? That's fine. And so on my way down, over here, well, at any given point, again, I can only keep going down. So if I was to, let's say I wanted to populate this first column, then I'll do this row and then I'll do the rest of it. So maybe my first step will be, I'll do rightmost column, rightmost column. Then I'll do bottom row. And then thirdly, finally, I'll do the rest. And if we were to do it this way, if I was to make my way down first, and like I said, I'll tackle this column here. The only way to approach, this from, approach the end from right above it would be to take a total path value of 2. The way I got this 2 is by saying, well, to get here, I know I already need the 1. To be standing above it is going to be a value of 1 in and of itself. So to actually get this value of 2 right over here, I need to sum these two values. By the same logic, this would be a 3, because at this given point, if I was standing in the top right corner, the only way for me to make it to the end is to go straight down, and that would cost me 1 plus whatever it cost me to get here, which is 2. And the way to get here just has to be this one plus this one down over here. All right, does that make sense? Let me know in the comments below if that isn't clear. But again, as we keep going, I think it'll make a bit more sense. I want to do the same thing in this bottom row here. If I'm standing at this position over here, right, the only place I can go, the only way I can get to the end is by going right. My total cost of going to the right is going to be the actual ending point, which actually I've got right here. That's what it cost me to be here, plus whatever it cost me to stand right here. It cost me 2 to stand here. It cost me 1 to get to the end. That's a total cost of 3, okay? Same thing here, if I'm standing at this corner, only thing I can do is to get right here, right? To get from there, I know I can get to the end and it'll cost me a total of 3. So if I'm standing over here, my total cost must be 4 plus 3, which is 7, okay? If I'm standing right here, the only way for me to get to the end is to go all the way to the right, which is a total cost of 4, plus whatever it cost me to be here, right? And that in total, plus what it cost me to get to the end from here, which we found to be 3, right? That's how we're getting the 7 over here. So first things first, I wanted to kind of take, or I guess, right column for you. It's always backwards, I always getting confused. Rightmost column, bottommost row, I'm filling those in first because there's only one choice that I can make there. Now, where things get a bit more interesting is in the rest of the array. I'm now standing over here. I know that it costs me to stand on this path right here. It costs me 5, right? 5 points right over here. It cost me 5 points here. How can I get to the end from here? I can get to the end from here by either going down or by going right. If you were in this position, would you go to the right or would you go down? Well, you know that if you go to the right, it'll cost you 2 more units to get to the end. If you go down, it'll cost you 3 more units to get to the end. So which one is the cheaper path? The cheaper path is going to the right. So at any given point, what I'm selecting is I'm selecting my, let's call it grid, and maybe it's ij, plus the minimum of, I'll call it right and down. This is the decision I'm making anywhere for the rest of this grid over here. I need to take the value of what it costs me to stand where I'm standing, plus the lower of the two costs to get me to the end. Either that'll be going to the right or that'll be going down. All right, let's keep going. I'm looking at this spot here now. This spot here, it costs me 1 to stand here. And the question is now, if I want to get to the end, I can either go down or I can go right. If I go right, it'll cost me 1, the one that's standing right here, plus 5. If I go down, it'll cost me the one that I'm standing here, plus 7, which is lower. 1 plus 5 is smaller than 1 plus 7. That will give us 6. All right, 2 more to go. I'm looking at the 3 right over here. It's going to cost me 3 points to stand here. If I go to the right or I go down, those are my only 2 options. If I go to the right, it'll cost me 3 plus the additional 3 of going right. If I go down, it'll cost me 3, this 3 right here, plus the additional 5 of going down, which is cheaper. 3 plus 3 is cheaper than 3 plus 5. So this would cost me 6 if I'm always choosing my optimal solution. In this case, our optimal solution is to minimize the total sum. Finally, we're at the beginning. Now this is where we want to be. We're at the top left. It cost me 1 to stand here, right? 1. Is it cheaper for me to go right or to go down? In this case, it's the same. In both circumstances, they're both 6, so it doesn't matter. But we're going to say 1 plus the smaller of the 2, which is a total of 7. That means that from here, my optimal route is going to cost me a total of 7. In this case, that optimal route happens to be 3, 4, 5, 6, 7, right? This one. Does that make sense? So that's how we're essentially going about solving this. The ultimate place we want to get to is we want to start at the bottom right, and say, if I was at the bottom right, what would it cost me to get here from my adjacent cells? Instead of saying, I'm going to be at the start, how do I get to the end? We're going to say, if I was at the end right now, how would I have gotten from one spot before? One spot that's just kind of adjacent and around me. And when we keep asking that question, we build it up and we kind of branch it out. This way our scope increases and we fill in the rest of the grid. And that's ultimately kind of the way we want to solve this. In its rawest form, this is a dynamic programming approach. The reason this is a dynamic programming approach is because it takes one problem and it breaks it down into sub-problems. If we were able to solve local problems, these local problems, so saying, if I was here, what would it cost me to get to the end from here or from here? And then how would I do that here? And really this formula right over here, this little piece of logic we're working with, we are solving smaller, more local domain problems than just the grander one. By solving these collectively until we get to the beginning, well, then we solve the whole problem. We've broken it down into sub-problems, and by the time we got to the start, then we were like, all right, we're ready to go. This is all good. We've found our solution. So the nice thing about this is as follows. This is an iterative solution, so no recursion. And the other thing is that it's our optimal time and space efficiency. To discuss those complexities, not efficiencies. The reason it'll take, so our time complexity here, our time is going to be O of n times n. The reason it's n times m is, as you see, we kind of touch all of these squares once. There are a total of n times n of them, n times m of them. There's no way around checking every single one. That's as quick as we can do it. Space-wise, it depends. Now, this is where you instigate a conversation with your interviewer and you say, if I'm given an input array, am I allowed to modify the array? If you are allowed to modify the array, you can make all these changes in place in the existing array, and that would be an O of 1 solution, right? Simple as. If you're not allowed to do that, what you might want to do, wow, I'm slurring my words today, is to create a new 2-dimensional array of size m by m, like the one you're given, and populate that one just like we did here. There is a slight way to optimize this, so I'm gonna go ahead and assume just for today that we're allowed to change the input array. There's a slight way to optimize how to get this into O of n instead of O of n times m, even if you're not allowed to modify. But I'll leave that for you guys as an exercise. I want to focus on this solution here in place. So this is the majority of the logic, and I think we're good to jump into the code now and see what that would look like. So the second one we said is going to be a DP solution. So work from the bottom right up to the top left, and find the cost to end from each given spot. And we said that the time would be O of n times n, which is a huge improvement, and space, if we're allowed to modify in place, would be O of 1. Else it would be something like O of n times m with ability to optimize to O of n, right? I won't get through all those details today, but I do want to tell you that it exists. So first thing I want to do is my standard error checking. And so let me just say error checking. Next thing the next thing we're going to want to do is to populate that right column. So maybe I'll say populate rightmost column. Then I'd like to populate the bottom row, and then finally populate rest of the grid. By the time we're done doing all this, we said that when we reach the beginning or the top left corner, we're just going to want to return that value. So we'll return 0, 0. There are ways to kind of put this all into one step and have a lot more checks going on, like if statements. I like to break it out. I think it's easier for me to think about, but feel free to optimize and drop comments down below on if you like the code factored, in a way that maybe seems more tasteful to you. For error checking, all we're really going to do is say if we're not given a grid, if not grid, we are going to return 0. Now, I want to populate the rightmost column. Well, for the rightmost column, I basically want to see my column is going to be fixed. So my column is going to be equal to the length of the grid, that's 0, so the length of the row, minus 1, that's going to be my column. And then I'm going to want to go through the different rows. So I'll start it from the bottom up, just like I did in that example. So I'll say for row in range, and then let's see, we want to do it from the bottom row, which is the length of the grid minus 1. We want to go all the way to 0. So we'll go to -1 non-inclusive, and we'll decrease by 1 every time. And we're going to say that row column is equal to, plus equals. So we're going to take that value that we have here and add the value down below. So we're going to add grid of row plus 1 column. And so again, the reason I'm doing that is if you think about how we built this out, we said that I'm never really going to be touching this value over here. I'm going to start from here and go upwards, and from there I'm just going to be adding the cumulative cost that it takes to take that one step up. So that's where we're kind of getting this logic. This will take me all the way up, and that should populate the rightmost grid, right? Now we're going to implement very similar logic for the row, and this time we're going to say that the row is equal to the length of the grid minus 1, because we're at the bottom row. I'm going to say for the column in the range of the length of the grid at let's say 0, minus 1, and again we're going to go to -1 non-inclusive or 0 inclusive. We're going to be decreasing by 1 every time. And I'm going to say that grid at some sort of row column plus equals the grid at that same row and column plus 1. So we're going to add the cumulative value in the column from the column to the right? And that's what we're going to be adding on every single time. This has now populated the first 2 steps. So our first step is done on populating the rightmost column. Now we're going to populate the bottom row. And when I say populate, I mean with those cumulative values. And finally, now we're going to want to populate the rest of the grid. So this is where we're going to do a double nested for loop. So I'll say for row in range, we want to start at the second last one now. So at the length of the grid minus 2, and again we're going to go all the way to 0. Make sure I got that right. And then for the column in the same range, we're going to start from the second last one. Minus 2, minus 1, minus 1. So we're looping all the way to the beginning. We're going to say that the grid at row and column, to that value, we want to add the minimum of its values to the right and down, right? So add current grid spot plus min of right and down, right? So the spot to the right is going to equal grid of row column plus 1. Rather, what I want to do here is have this all in a minimum statement. Oops. Oh boy. There we go. So we want the minimum of the spot to the right and the spot below us, which is grid of row plus 1 and column. And that should be it, guys. So if I haven't made any mistakes, again, all that we're doing here is we're really just, we're populating the rest of the grid. So in this case, it's these, this top 2x2 grid after we've filled out the rightmost column and the bottom row. Those cumulative values will build up such that when we get to the top left corner, we're done. And that's our optimal least cost path to get to the end. If I run this, clearly I made a mistake. So let's see what we've done here. This is in line number 19, and we're in the rightmost column. We want to start from, oh, excuse me. So right here, I want to start from the second last one, not the last one. Okay, we do not want to populate that last bottom right element. So my apologies there. I'm sorry if that was confusing. I made another mistake here, and I don't know what I've done. I'd really like to not have to record this again. So give me one moment here. Okay, just caught it. I'm a fool. I'm not returning 0, 0. I'm returning grid of 0, 0. I'm sorry, guys. So for anyone who was yelling at me while you were watching that video, I'll take that one on the chin. That's my bad. And there we go. So now it's actually solved. Super minor, dumb mistake at the end. Now, I know this was a bit of a longer video. We hit just about 20 minutes. I really wanted to make sure we get the full in-depth essence of what's happening here. If you have any questions about this one, if you want me to answer anything else, drop in the comments down below. Let me know how else I can help you guys with your preparation for all your upcoming tech interviews. It's been a pleasure, as always, and I'll see you guys next time. Peace.